So Tristan Watson. All right. From Swansea University. Tristan got his chemistry degree and his materials engineering degree in steel technology, I understand, from Swansea University in 2005, about. After getting his degree, he moved on to Core Strip Products, which is now called Tata Steel, I think, or a part of that. Working on steels basically and product development over there, and he got very interested in that time in steel and coatings and how they behave and that sort of thing. And he returned to Swansea University as a research officer and actually worked on dye-sensitized solar cells, very dear to my heart. It's where I cut my teeth many years ago, so this is great to see. And is currently a professor at Swansea University, and he's leading the specific Innovation and Knowledge Center over at Swansea, and is really focusing on thin film printed PV, developing new technology for manufacturing of solution processable photovoltaics, such as perovskites and OPV and other technologies. CZTS, I believe you work on too, and these sort of emerging technologies. And really characterizing and understanding these, but with a major focus on understanding how to scale up manufacturing and how to really do the manufacturing of these new technologies at scale. And so today he's going to talk to us about manufacturing perovskite solar cells and modules using carbon electrodes for scalable technologies. So take it away, Tristan.
Wow, thank you. And thank you so much for the introduction. It's really nice. And dare I say, actually, when I started in the field, I remember reading your papers early on.
All right.
When I converted from being a steel researcher and I tried to understand what an IV curve was for the first time, I remember your papers well. So it's actually nice that you've done the introduction. It's really lovely to be here. And, you know, I'm a great enthusiast for webinars and for knowledge sharing. So I was delighted to hear from Joe and Laura to give me the invite to come and speak to you. So hopefully over the next sort of 40 minutes, I'll say something that piques your interests or engages further discussion. And this is my perspective on a lot of what's going on, and it's the research from Swansea University, and other places do it different. And I'm a huge advocate for not necessarily ever narrowing the field. So I'm very uncritical of lots of the other approaches that people do. This is just our approach. And we think it's a good one. And you may or may not disagree, and I'd welcome those sorts of interactions as well. Okay. So the first thing to note is that none of the actual work that you'll see today was carried out by me. It was all carried out by these fantastic bunch of people that we've managed to convince to move to Swansea. You'll see the picture on the left was the one day of the year where it was sunny enough for us to go outside. And so we thought we'd try and misrepresent the weather in Swansea. As a Brit, I'll come back and I'm sure mention the weather many times throughout this talk. I just can't help myself. So yeah, there's the guys doing it. So a little bit about Swansea. It's in Wales, so it's in the United Kingdom, it's its own country in Wales. So yeah, I'm a passionate Welshman, Welsh speaker, and Swansea is that little dot on the map there. It's a couple of hours away from London on the train when they're working. And it's a rather nice place to come. And it's I'm happy, very happy to host and have people visit us from Swansea to come and see what we're doing. Some interesting things about Swansea, which I just touch on briefly, is that apparently the very earliest work on the fuel cell done by Grove was done in a basement in Swansea somewhere. Dylan Thomas is a famous author that was his hometown is Swansea. We have got some of the nicest beaches in Swansea. And in fact, we managed to upset the Australians once upon a time when one of our beaches came ranked in the Lonely Planet above Bondi Beach. And their response to that was, fair enough, but at least it's sometimes sunny in Australia and never sunny in Swansea, which is absolutely accurate. Once upon a time, we had a Premiership football team, but they got relegated a while back. So I'm thinking I might have moved that picture. So that's Swansea. And then within Swansea then is the specific Innovation and Knowledge Centre. So I may have mentioned this to some of you before, but we love an acronym. Everybody loves an acronym. And in fact, specific is an acronym, and it's cost us quite a substantial amount of our research budget to come up with this acronym. It's the Sustainable Product Engineering Centre for Innovative Functional Industrial Coatings. So I think 6 months of a PDRA well spent coming up with that acronym, I would say. And that's what we do. So it's functional coatings. that can be applied onto buildings. And that's the sort of message that we've tried to stay true to. How do we develop new energy materials? How do we put them into full-scale pilot manufacturing? And also then, how do we connect it up with the final usage, so the application of those? So to do that, then we have pilot manufacturing, not so dissimilar to a number of other sort of pilot lines that you might find. We have near-infrared and some photonic capabilities, as well as sheet-to-sheet processing and roll-to-roll processing. And this is all within a clean room in Swansea. And what happens when we produce things from this line is that we then try to integrate them into a meaningful environment, whether that's a solar facility for testing or actually directly integrate into the building. So you'll see one of the and a lot of these units are movable in and out. So our roll-to-roll line there, actually too big for perovskite on the left, was once designed for making dye-sensitized solar cells in a project that Tata were involved in, about well over a decade ago, in fact. But nowadays we use it to prototype some layers, and we have another pilot line, which I'll talk about later, which does our perovskite, which is more narrow, so we use less material. In order for us to really develop test cases for these, we actually then went and built active buildings. So we wanted to demonstrate that you could make an active building that could power itself, even in the UK climate, even in the Swansea climate, and could be actually assembled relatively easily. So we built our very first active office, an active classroom, a single tier and second tier building. We then subsequently exported that type of approach to a village in India, where they also have an active building, and that has energy technologies throughout, which capture, store, and release. So we have PV on the roof, fully integrated into the roof. That's second generation SIGs that was procured, I think, actually from the US, and laminated into the roofing product. We have lithium, sodium ion, redox flow batteries that power the buildings. And then we actually have coatings that heat up the floor as well. So simple carbon coatings that when you turn them into a Joule heating system, they can actually provide really efficient, zero loss heating directly from the battery. So PV to battery to heating. Actually, the carbon film that we use in those floor tiles is actually the same carbon we use in our solar cells, ironically. Not intentional. So what we're trying to do then is create active buildings and then monitor them as well. So we collect every single bit of data that we can from the building. We understand how the solar cells perform, how the batteries respond. And one of the things that we've ended up working on a lot in understanding this holistic journey is that there are experts in certain subjects and certain areas in terms of installation, but they're rarely brought together. So when we wanted the PV installers to talk to the battery installers, to talk to the heating, to talk to the solar thermal, to talk to the other various, that was quite challenging, and the systems didn't necessarily exist. So we've come to try and link those people up to try and say, okay, if you wanted to create an active building that was completely independent of the grid, not disconnected from the grid, I should say, but over the course of the year, capable of being net positive, then you need to get these people to talk. And these buildings, although they're in Swansea, in the rain, they are, over the course of the year, net positive. And there's a really nice story with these buildings once when we were about to have a power cut in another part of the university about 100 meters away. And we were really concerned that our TEMs were going to go down and suffer failure. So we ran a big electrical lead all the way from our active buildings right the way down to our laboratories to keep our TEMs running for the 2 or 3 hours that we needed in order to get the university systems back up and running. That was a couple of years ago, but it goes to show that, there's huge value. So my message here, I guess, is that when we're thinking about the scale up of, emerging technologies, understanding the application as well is quite interesting. And I like to reflect on the community that, I've found the PV community to be an incredibly welcoming environment. And I feel like we're all on this really exciting journey together. But then I like to reflect on how far we've come as well, to a certain extent. So I love looking back in time, and the 1912 Baker electric car is a really good example. So this actually picture's not from 1912; it's from 1960, when they put a solar panel on top of the Baker electric car and demonstrated that you could, to a certain extent, power some of the electric battery from PV. So this picture is from the 1960s, but the actual electric car, of course, is from the 1912s. And we go forward to the technology. You can see the World Solar Challenge there, which requires a driver of a certain BMI in order to function, not a BMI that I have. Unfortunately, given my size, you can't see on the screen, but I wouldn't be able to go very far in that electric car, I don't think. But it does work. And then even more than some other innovations, such as the Lightyear one. I don't think it's commercial yet, but I'm excited to see what they were able to do in terms of adding range using PV. The DuPont Gossamer was something, again, that you'd probably need to be quite light in order to be allowed to travel on. And then we go to the Solar Impulse, which does some really great stuff in 2015. This I really like. So when I evangelize about buildings as power stations or integration of technologies into buildings, I always have to remember that this is nothing new. Not only is it nothing new, it's very, very old. So almost 40 years before the Solvay conference on electron and photon, Charles Fritz was, bunging some solar arrays on a building and measuring some of the output, which I think is just an incredible lesson in, having a go at things. Having the full picture of a technology isn't a prerequisite for having a crack at deploying it or testing its applicability. And I think it's a great example. And we waited, quite a long time after that before we eventually saw them ubiquitously being installed, as we do now, which is a great, great step forward to, my predecessors then in this field. And in our area, then we have full roofing integration of second generation. So we work with a former spin-out company called BIPV in South Wales, who take on steel roofing, and then they apply SIGs, vacuum deposited SIGs panels onto the roofing in order to develop a product. And the roof is actually assembled in a day. So all of the processes for laminating and developing the PV is done off-site. And then this roof, and it's it's flat at the front and then curved at the back. We can see we wanted to try different ones. So we built the classroom. This is the building in the foreground first. And that was a few years of existence before we wanted to test what it would be like if we curved the product. And so this is now fully functioning and it works really well, and people occupy that building and it's used, and it's powering the use of that building. So it's a really exciting concept. I want to make that PV. I want to be part of the grouping of people to make that PV. And I would like to make it in the UK. I'd like to make it in the Wales. I'd like to make it in Swansea. And I'd like you to be able to make it in your hometown, in your home city. And so I'm going to talk a little bit now about how we might do that. And perovskite is a really exciting, as you already know, presumably I'm going to be preaching to the converted a lot today. But perovskite is incredibly unique in giving us this opportunity for the first time in quite a while, where we can potentially democratize the manufacture of solar energy. The way in which we can do it is going to be different to where we are now. So this is perhaps a relatively familiar transition of the state of the art, where there's some democratization of, or rather distribution of, quartz mining, but then we start to see a narrowing in terms of the supply chain for a particular economy. And I'm not critical of this, just to be clear. This is not me saying, oh, we need to do something about this, because without this process, we wouldn't have PV on our roofs. Okay, so we have to recognize that there's an economy that is producing an enormous amount of PV, and we need that PV to continue to be produced, but we need a lot more. And when I think about the additional amount of PV that we need, I want to make it. I want us to make it as well. And I think that's where perovskite comes in. So we've seen this, credit to NREL, of course, for this excellent data of the journey of silicon over the years. I've never worked in silicon, but I'm continuously impressed by the work that's done in that area. But if I wanted to do it in Wales, I'd need to go to our First Minister in Wales and say, I really want to have an industry that makes solar panels. Have you got a couple of billion spare for me to create the supply chain? Because I don't want to buy wafers in and stitch them together. I want to make everything from scratch. Can you help me? And the answer would be quite clear about that. In that not many governments have deep enough pockets to be able to do that. The US might be one of them, but certainly in Wales, for example, we don't have deep pockets sufficient to create a supply chain of this nature. And in fact, even if you took the latter stages of the supply chain and you imported everything else. That's also quite challenging. So thankfully, though, over the last 10 years, we've been on a really stellar and interesting and exciting journey, which has awoken the interest of many in the potential of next generation solar to do something different. And so I've asked DALL-E and ChatGPT. We mentioned this as we were talking in the virtual green room earlier. What would it look like? So I asked a ChatGPT to come up with somebody manufacturing solar using traditional Welsh dress. So there we have. This is the vision then that I that I would like to see delivered. Maybe not those sorts of panels that this lady is working on, but something slightly different, which I'll talk about now. And of course, by virtue of creating a way in which we could manufacture in Wales, it's creating a way in which it could be manufactured anywhere. And that's also something I'm passionate about, not just in the UK, but in America and South America, Africa, all over the world, I think is what I want to see happening. So the question that I'm going to pose throughout this talk is, can perovskite deliver democratized PV manufacturing? Yeah, okay, so let's sort of challenge that concept. One of the things that we need to do is we need to move on from the work that's done in the spin coating. Now, as a process engineer, which is what I would maybe describe myself, a solar processing engineer for next generation, and if I was to put a label on myself, we need all of the incredible work that's being done elsewhere of people toiling in glove boxes and fume hoods with spin coaters for hours on end to understand the fundamentals, to understand the basics, and to help us develop the material set. And we are nothing without that work. So we can't engineer and scale up nothing. Thankfully, there is an incredible wealth of new movement, new technology, new developments in this field that are coming through that we can access, and we can challenge and develop the challenges of scale for those materials. So we need this work in spin coating. And then what we do is take that forward. How do we go from something such as a spin-coated device to a pilot line to a roof, a real roof? And I think we are on that. We are well and truly on that journey at the moment. From my perspective, then my group is actually split into two, and so this talk is actually split into two, where I'm going to talk about roll to roll. Actually, second, I'm going to talk about sheet to sheet first. So I'm going to talk about roll to roll later. Where you might consider that to be high throughput. And I'm a real enthusiast for the concept of ink in, solar module out, where as long as you keep your substrate topped up, as long as you keep your ink topped up, if you've got your right settings, the power and the wonder of a solution-based process is that production should continue indefinitely if you've got the conditions right and everything keeps going. Of course, it's never like that, but that is the ambition. Ink in, substrate in, solar module out. And that's something which perovskite absolutely lends itself to. The second one then is sheet to sheet. And this is an interesting one because I think, although you might have low throughput, the cost for a sheet to sheet line is really quite low. And even the pseudo manual transferred sheet to sheet line is really low cost. And that, I think, is something that I maybe think could make some really big changes, and that's something that I welcome some criticism and some comment on that. When we're thinking about the scale-up route, the wonderful thing that we encountered as process engineers is that there was no rule book about how to treat these materials back in 2015. So when we received our when we synthesized our first pot of simple MAPI, we really looked at each other and went, right, okay, so blade, inkjet, slot die, spray, dip, syringe, how are we going to do it? The ultimate answer, if you look in the literature, is all of them. They can all deposit layers really well. Almost all of these, in fact, I think would deliver, a 15 to 20% device in a lab. And so that's great. It sometimes leads to confusion, and it sometimes leads to us having to make, I don't like making big long-term decisions particularly, but we did have to make some, and we made a decision about slot die coating, which we'll talk about later, and screen printing. But the reality is that, again, versatility of perovskite is such that, as you know, it lends itself to a wide range of processing techniques. So let's talk a little bit about sheet to sheet. One of the approaches that I've always tried to keep in developing a manufacturing pathway is how low can you go? How cheap can you make it? Is there ever a scenario where any district government or any local, city government could build a factory for solar modules? Is it ever going to be that cheap? And I think that it possibly is. It depends again on the calculations for megawatt production, etc., and payback time for the factory. We have done calculations in that to make sure that we're not talking complete nonsense, I think. But is it feasible? So when we looked at it, we were already pretty familiar with screen printing. So we wanted to use screen printing as a mechanism for making these devices. And there was already some early stage work being done on this particular device structure, developed by Hongwei Han in Wuhan in China, who's gone on to do some incredible work in this area. It's a triple mesoscopic stack where the fundamental premise of it is to build up layers using screen printed pastes of titania, zirconia or alumina with a thick carbon on top. That's a porous structure when you fire it. So you fire it and you turn it into a porous structure. So you've effectively got a completely mesoporous architecture. There's no spiro in there. There's no complex processing conditions. And then you drop the perovskite and it trickles through the device stack. So this is something that we've traditionally been quite keen on for the simple reason of a reduction in cost. Of the ability to make it. Screen printing is relatively low cost. So this is an example of us making them. Hopefully the video is running reasonably well. This is us sped up, but effectively some examples of mass production. This was probably a 20 to 30 module run, I think, where we print the layers and then we heat them at high temperature. What really struck me was the simplicity of this process. And so we explored whether an existing industry could do it. So, there are people as we speak who are screen printing somewhere in the world, and they're likely doing it using T-shirt screen printing processes. So we wanted to understand, is the screen printing processes required to make this device module, this stack, capable of being done at a screen printing company that didn't really understand it? So thankfully the titanium, zirconia, and carbon are they don't have toxicity issues. So we could go, and we went to this company in Mexico near Merida, and they had no problem in depositing all 3 layers in a sort of mini module structure. And we consider that to be about 80 to 90% of the actual module construction. So we took some FTO glass and they deposited the 3 layers down onto it, and it worked really well. That's not to say that there's no high technology to understanding these processes. So our team in Swansea, we still feel that there's opportunities for us to do good work in the printed layers. So we run fundamental analysis on the potential for the deposited layers via screen printing. So we visualize the screen printing process. We optimize the printed layers in order to make sure that we get things like a clean pull off for the way in which the screen leaves the TiO2. That leaves the TiO2 to be flatter, where the zirconia can go on top of it in a nicer way, and then the carbon doesn't show so much mesh marking. So there is ways in which we can add percentage values onto the mechanism by bringing in more advanced technologies. But fundamentally, the process is the same as that used in a textile T-shirt screen printing project. And I was really proud of the title that we had for the work that we did there in the grant. So not only do we like titles, we like acronyms, we like titles. That was called Textiles to Terawatts. So I was really pleased. I didn't come up with it, I should say, it was somebody else, but I really liked that. And we did demonstrate that you could take a textiles industry and potentially, who knows, down the line produce something just based on an alliteration. There we are. So we also heat them up. So this requires some process engineering in order to be able to get a high temperature process. You can heat the titanium and zirconia up together, but you typically then need a separate heating step. So concede that you do need a high temperature process in order to make this work. And that can come with additional energy costs for sure. So I think there is a recognition that there are issues there that we would like to resolve. And when I come on to roll, that's an entirely low temperature process. Can we do interconnects cheaply? Well, can we do them via mechanical scribing, for example? So this is us mechanically scribing a 30 by 30 module using a knife. a blade. Now, behind this work, of course, is understanding the right pressure of the blade. And this was somebody's project for a few months to understand the right pressure. But it turns out that we can scribe these really quite cleanly using a XYZ worker bee type platform, and we can do these in batch processing. So no problem with the interconnects there. And we recognize, though, that with mechanical scribing and not laser, you can do it with laser. We just wanted to make sure that we could really show low cost. We get to about 85% geometric fill factor with the mechanical scribing. So it's not 96, 98, which is what we'd really like to see. And I think you probably could get that with laser, provided your contact resistance between the carbon and the FTO is, that's another talk, I think. But at least with relatively modest cost, you can do it. What you do next? Well, then you take the prescribed triple layer, which before you add the perovskite is as stable as you need it. So you could manufacture this in another country and ship it across the world. It's completely stable because it's an inert scaffold. Then you drop your perovskite into it physically by dropping it. We use the same type of worker bee system, an XYZ stage to solution drop in the perovskite in this sort of system. It was done manually, very arduously done manually in the top left-hand corner. Nowadays, we do it via a droplet system, and that's all we require. And we've been able to demonstrate 10% module performance active for 80% geometric fill factor for these modules so far. And there are things that will take it much further higher than that. So maybe, hopefully, I've demonstrated that with a screen printer and an XYZ robot and an oven, you can make meaningful modules that produce meaningful amounts of electricity. I think with these three simple processes, that it won't look like this in the factory, because someone will come along and for another low-cost option will add 2% on, or will add 1% on, and that will come later. But it's the start, and I think fundamentally it provides a really good framework for what might come after if you chose this structure. But I think it also gives the message that perovskite generally has a really strong potential in the future. So the other thing then is, where do we want to make it? Do we want to make it in a really precise environment, or do we want to maybe be able to make it wherever we want? So one of the other areas then is solvent toxicity, which is really important to us. So in the typical device stack, this uses gamma butyrolactone, which is relatively on the lower side of toxicity if you're working with perovskites. But it can't be bought in some countries. So in Mexico, where we've done some of this work previously, it can't be bought because it's a starting material for drug manufacture, apparently. So it's challenging to get that material in. It transpires that its sister, gamma valirolactone, is even lower in toxicity, is biomass derived, and is no problem in terms of importation, etc. It has lower environmental toxicity, is biodegradable, and has no legal restrictions. And that works just as well as GBL. So this is something which is relatively new for us to find out. You do need to add, for rheological reasons, you do need to add about 10% methanol into it. But with 10% methanol, you can really make devices which are just as good, if not in some cases better, than the incumbent GBL type solvent, which is normally used to make these in labs all over the world. This is something that I'm really interested in as well. I don't want us to have massively expensive clean rooms either. I would like us to make a device that doesn't mind dust. That would be cool. Yeah, if we didn't really have to worry about having a clean room, that would also mean that we could make it potentially in textiles manufacturing environments. And so we've done some work in developing or replicating what we think might be various levels of a dusty environment, whether it's a standard lab, a clean room, a steel plant, for example, a textiles manufacturer, and we understand the sort of dust volumes there. And so we're exploring which of the processes are more sensitive to having a dusty environment, such that if you were building a factory, you might be able to say, okay, for 75% of this factory, we don't need it to be in a clean room. So we only need to invest in the clean room for this fourth of the fifth process, because this is the one that really needs to be done sensitively. Because once we've got a layer on top of that, it's effectively protected from any further dust. So we've been exploring this. So we've been looking at putting dust in different layers. It helps that these are really thick layers. So the titanium, the zirconium, and carbon are all up to sort of 12 microns in total. So it does help us to understand that. So we've been putting in dust at various levels and at least early stages. For example, if we put dust at the titania interface with the zirconia when we're printing, so we effectively print it in a dusty environment, and you can see that the dust is formed in this bottom left-hand image, the efficiency doesn't change. So it turns out that the perovskite, and we don't know why this is yet, but the perovskite is enough if it forms around the dust particle. It doesn't prohibit the overall device performance. And that's already quite interesting. So we're looking to apply that now into planar devices, which we think will be more sensitive. And what we'd like to know is, what is the threshold of dust at which the device really starts to show poor performance, or really starts to show a drop in performance? Because then that's the cost of your extraction. That's the cost of your clean room. And hopefully that's actually going to be quite low, the cost, if we can prove it. So this is another interesting area. And this came about from one of my excellent technicians who wanted to do a PhD. And I asked her what she was in, what was she interested in? And she said, well, she's interested in the conditions in the lab and the cleanliness of the lab, because that's what she'd been doing a great job of. And it transpires that actually she can do some meaningful research in that area as well. So that's some really nice stuff, which we're looking to publish in the next few months, I hope. Then it's a case of performance. So how can we measure how these devices do? So we've made some modules and we've made some arrays and we've sent them to various places. And we've done some of the measurement at home in the UK as well. One of the things that we wanted to do, again, is even make the QA low cost. So how can we do QA for modules? It turns out that optical analysis can pretty much tell you straight away whether your device is going to work. And almost from measuring the infiltration, you can predict what the efficiency is going to be, because that's one of the biggest challenges in the device. You can also understand mesh marking defects. And so we can use QA using optical analysis, again, keeping the costs down, end of production line, monitoring of consistent performance of the module. Right. So how do these perform outdoors? Well, they're about 10% outdoors. We found it quite challenging initially to be able to say, how can you measure outdoors and indoors at the same time of the same module? Because very few people in the UK have large area solar simulators. And it turns out that actually having a 30 by 30 or a 50 by 50 xenon arc or LED system was actually quite challenging. So we didn't know how to measure our modules. So we said, right, we're just going to have to put them outdoors. If we want people to think that we're doing something credibly, we need to present how we're doing. So we'll put them outdoors. It turns out that during this time, again, lots of work being done elsewhere, and Hongwei Han's just released a paper, which I think is in Nature Communications, or one of those journals, showing that these carbon devices now have gone over 20%. So they were always lagging behind. And there was less interest in them because they weren't putting those efficiencies higher, but they're now at 23%. So it's really promising for these sorts of low-tech type manufacturing processes. We then did get a solar simulator, and this is probably one of the most important bits of data that I got this year, which was that confirmed that 600 watts per meter squared on AM1.5 in an LED solar simulator gave us the same rough value as what a 600 watt pyranometer in our external weathering gave us as well. So we collected the data at the points of 600, and then we measured the same module indoors a day after each other. And it turns out that they are approximately the same. So they're not a million miles away. So when I've been presenting outdoor data over the years, I'm not far off what you'd get if you'd measured it with a solar simulator. So then we set about testing it. And as I mentioned to Joe and others in the past, Swansea has a particular climate. A winter in Swansea is wet. And for some reason, we chose to put our modules out in January because we couldn't wait. We were too excited. So we didn't want to wait for the nice weather. So we put them out right by a steelworks in a coastal area in the rain. And in fact, they do work. And I've presented this before, that we do have reverse bias issues sometimes when we have depositions from animals nearby. That it turns out that this particular device stack has been published as being relatively resistant to reverse bias. And it transpired that even when we didn't realize that our modules had dropped in performance, that they had actually still continued to work once we cleaned them off as well and everything. But that was quite an interesting lesson. This is our outdoor test, which I'm happy to discuss and share. I understand that there's probably plenty of people on this call who know this work even better and have set up some really nice facilities in NREL for testing. We have our own testing under this mechanism, and we do it slightly differently. So we do an IV trace every 5 minutes through the daytime on our panel. Then we hold it at the maximum power point from that IV trace for the remainder of that 5 minutes, and then we run another IV and do the same thing. So it's a version of maximum power point tracking that is done with much lower cost equipment. So it's really done with the software rather than with teetering either side of the maximum power point. We think this is okay. I'm happy for people to criticize this as well if they feel that it's not justified. I think that every 5 minutes running a JV scan is probably quite a heavy system for perovskite. But I'm happy to stand and to improve our systems if that's appropriate. So we test them all simultaneously. These are the conditions in Swansea. So they have dropped below zero in the earlier part of the year. And you can see on the right then, the pyranometer suggests that we don't get a huge amount of sun. It sometimes gets up to 600, but we won't reach 1,000 probably until we're starting to reach it now, actually. So today I checked the Grafana plots for the modules, and we did reach, I think, 1,000 today briefly. So we are getting data on one sun, but it's mostly less than that in Swansea at the moment. And this is the results for our tests. So sorry, forgive the diagram there. I must have been copying and pasting it into a slide from previous. I'm not trying to hide anything. The lines are just the same and behind that. But effectively, the module has been consistent since we put them out in January over the last 4 months. And I had a look at them today online, and out of the 7 modules, 4 of them have failed because we were trialing new encapsulation processes. The 3 that didn't have the encapsulation process that we thought would work, and they're still working now 4 months later, relatively flat, 30 by 30, 517 square centimeters. So we're excited about that. Okay, so that's work on sheet to sheet. Now I've got 10 minutes, I think, maybe, or less to talk about roll to roll. Thank you. Roll to roll work. So I'm going to skip through this as much as I can. It's a different part of my team, although they do talk. I don't keep them in different silos and not allowed to interact. But roll to roll has slightly different challenges. And these are what I would describe as some of the ones that we need to think about when we're working about roll to roll. So this is now moving away from FTO glass, which is the first part of my talk, onto flexible PET based, ITO PET type flexible perovskites that are done via roll to roll. And what I mean by roll to roll is that you have a continuously wound roll process where the PET comes on and continues to go, and it'll run until your substrate runs out. We have a Cotima system, which is quite small, but it allows us to really get in and work out what's going on. It's about 10 millimeters wide, this particular production run. And it's in a humidity controlled. We controlled it at about 30% humidity and clean room. It turns out that a clean room and a humidity control is actually quite challenging and quite costly. But one small room in our labs in Swansea is completely humidity controlled and temperature controlled. And it's also by the sea, which means that we can work all year round, which is really helpful. So we have the standard systems of a Corona unit, a winder, an unwinder, web guiding, and oven. And we use slot die. So we decided a few years ago that we really go for slot die coating as a technique. This is an old experiment where we were depositing MAI down onto lead iodide in a sequential slot die process, which is perfectly feasible. We don't do that anymore. We only do it in one step nowadays, but it is possible to deposit slot die onto slot die. And the technique, I won't go into the technique because I realize that I've been too long, but it's a good one. I'm happy to talk to people who are interested in slot die coating. We've spent a long time trying to learn how to do this properly. Different layers have different challenges. So do we go for NIP or PIN? This is, do we work with 2 packs, which is quite thin? Do we work with SAMs, which are, single layer via slot die, really challenging? Do we dip it? How do we do it? All of these questions we think about on a daily basis. We have a standard device architecture now, which is relatively straightforward. It's tin oxide, perovskite, PDOT, and then carbon. And I'll talk a little bit about how we came to those conclusions. Slot die coating of perovskites, again, is its own multi-hour talk in terms of the crystallization and process improvements. We've managed to work with ACN MAPI and THF MAPI. We've developed FAPI processes that we're not quite ready to talk about yet. We still got some checks to do before we confirm that we're able to do it. But certainly we're trying to move up the hierarchy of perovskites without compromising on toxicity. It's relatively easy to move up to FAPI if you're comfortable with DMF. But you really can't get your head near the slot die coating head to work out whether your meniscus is settling properly if you do it DMF. So you almost can't ambient process. You couldn't run DMF in this lab. Okay, you wouldn't do it. You have to put your slot die into a glove box. All right, really, really technically difficult to do it. So we have to work with low toxicity solvents. And ACN is on that borderline. THF is also we consider to be acceptable based on workplace exposure limits. And we can do different things. We can add acids to allow the grains to grow, and we're processing if we've got a limit in the oven drying. We can use air knives, which is a popular technique in roll-to-roll processing, where you blow air onto it. And this has shown improvements. So this is the work. We are starting to do some green solvent work on FAPI, but it's still early days, and we haven't transferred it to our roll-to-roll yet, but it looks promising. This allows us to do more stable materials. And the big challenge for us then is to go to fully roll-to-roll devices. Excuse me. The challenge with fully roll-to-roll is that it often isn't fully roll-to-roll because we end up not putting the electrode on at the end. We end up taking it offline, walking it down, or we did, walking it down the corridor and putting some gold on top of it and then considering it to be a finished device. Now that, by any stretch of the imagination, is not ink in, solar cell out. It certainly isn't. It's ink in, partially made, solar cell out. So we really worked to try and overcome this. And lots of groups were claiming fully roll-to-roll, including us, I might add, when in reality, the electrode was not part of the process. And we really wanted to overcome that. Some really nice work on carbon was something that we decided to try and do. And there was other people working on carbon offline, not in roll-to-roll. So the work by Dave Bine and Ershad Pavazian and Rahul Patadar was to take vacuum deposited to translate from vacuum deposited to inline by developing a carbon alternative that could be printed via roll-to-roll. And the challenge with carbon via roll-to-roll is it's not quite the same as doing it via sheet to sheet. You've got to put it down onto a solvent. You've got to get the solvent compatibility right. The polymer's got to be right for slot die coating on a roll-to-roll condition. You've got to make sure that your carbon contents are right for your sheet resistance. And you've got to make sure that the ink actually remains wet during the coating process. You can't have it dry too quickly. So you've really got to get your solvent blend right, your rheology right. You've got to have it drying at the right conditions. And if you get all of those things right, you could, in theory, then deposit that final layer using roll-to-roll processes. So we did some initial development. This is Spiro Gold. This is what we would advocate as being the one that we wanted to catch up with. And when we put carbon down directly or put it down on Spiro, it didn't work. And we initially thought that we were washing away the Spiro. It transpires that we think actually we weren't washing away with the Spiro. We were washing away the Spiro additives because the Spiro was still there when we measured it, despite it not working. But none of the other lithium TFSI type materials were there. So we're still trying to understand what on earth was going on there. But it's quite interesting anyway that we observed that. So then we decided to put a carbon layer in a PDOT layer in between. Now this isn't PDOT PSS, it's a slightly different type of PDOT, but it acts then as an interlayer between the carbon and the perovskite. And it really does sit there covering it in fully, but at the right thickness without allowing any penetration between the perovskite and the carbon, which might be problematic. And that worked at sort of lab scale devices. So we went and we tried other interlayers as well, other than PDOT. PTAA didn't work very well. Spiro didn't work very well. P3HT did work just as well as PDOT. So we can use P3HT in that scenario, but we stuck to the PDOT system for this experiment. And with some optimization in lab scale, we managed to get up to over 14%. And we managed to identify the homogeneity within the device, that the PDOT was really covering the perovskite properly. And then we were able to demonstrate that it also wasn't a waste of time in terms of lifetime. We wanted to make sure that it at least wasn't worse than the gold. We didn't want to build in an instability, and it turned out to be better. So this is unencapsulated, 25 degrees at 70% humidity, showing a T80 of well over 1,000 hours in terms of it being unencapsulated. So this is MAPI, unencapsulated in 70% humidity with that hydrophobic carbon on top. So there's really promising potential there. Final few minutes. We wanted to then move to full device processing, which meant depositing every single layer sequentially. We've only got one slot die coating head, so we had to make sure that if we were going to be serious about presenting this as a real viable industrial technique, they had to run at the same speed. So we really wanted to imagine it was one head, one oven, one head, one oven, one head, one oven in a complete process. So they had to be deposited at the same speed. And that's what we did. Only 1 meter per minute in the initial trials. And we demonstrated that we could get a working device fully slot die coated right the way up to the carbon that was about just over 10%, almost 11% in terms of full device processing via roll-to-roll. And this then gave us a single strip proof of concept. Now, this is great, and it's really important for us to be able to demonstrate these sorts of steps forward, but it isn't a module. It's not a solar, it's not a ink in module out. It's ink in interesting solar cell that you can write a paper about coming out. So we really wanted to show, how do we do interconnects in roll-to-roll? Well, there are a number of ways in which you can do it. The best one, if you've got the equipment, which we don't have inline, but some do, is laser ablation. That's probably the way that we'll see it in the future. You can do it via mechanical scribing, and I'll skip forward. I presented this recently. You can mechanically scribe on PT, ITO, but it's very challenging. It's not very reproducible, but you can use a blade on PT. The best way to do it is probably with interconnect. And what that means is effectively overlapping the layers by moving the substrate in order to do that. So you use a web guide, you deposit a layer, and you deposit a layer slightly offset, another layer offset, another layer offset, and then eventually your carbon crosses over onto the next patterned layer of ITO. And then your active area is relatively modest. But it's possible. You don't need a laser, you don't need a mechanical scribe, you just need good control of your web guide. So you need to be able to make sure that you can move your web. So when you see something like this happening in your roll-to-roll, you know that you're never going to get a good geometric fill factor if you're moving 0.4 millimeters every time your web runs and you're not doing anything on it. So we've solved this problem, and now we have quite a sharp web guide. And so we can now complete the module fabrication using this process. So this is tin oxide. Then we've shifted it a little bit more, and then we can deposit perovskite. We shifted it a bit more, we can deposit the PDOT, and we shifted it across then so that the carbon can come right across. So that then represents fully inline manufacture using slot die coating, which we did in March of this year. Clearly, low geometric fill factor, low performance, but we have a fair idea about where we need to go next in order to push it up into that top right-hand quadrant. And that top right quadrant represents ink in, commercially viable solar module out. And so that's what we hope to achieve over the next few years. Thank you very much for listening.
Thanks, Tristan. Yeah, I mean, one of the reasons why we were so excited to have you is I think, you know, some of the things that you presented in terms of the vision that you have for what can be achieved from a manufacturing perspective is, you know, just really appreciate it. I will start with a couple of the easy kind of questions, I think, to get into, but do post if you have additional questions, because otherwise I will certainly take prerogative, as I have lots of them myself. But we had one, which was if you could just describe a little bit the corona treatment for those who may not be familiar.
Yeah, so we don't, the corona treatment is plasma treating in a way. It's not quite plasma treating, but it allows us to just make sure that the surface is clean. So we don't, it's a really good point, because we do a lot of plasma cleaning offline when we make devices, and we're still not quite sure whether we're cleaning or functionalizing the surface. So the corona treatment isn't essential if you understand your surface energies of your incoming substrates. It's not essential. If you want to adapt it and play with it, and maybe change it a little bit, if you feel like your ink isn't going to be suitable, then you can use the corona treatment. We don't always use it, I should say.
I mean, do you feel like it gives you a little bit of flexibility in terms of kind of the local process conditions and kind of normalizing?
Yes, very much, very much. But also, you know, we've done some things before where we've dipped the coating into a solvent before coating in order to try and change the surface energy. So one of the things that, you know, a contact angle measuring device is essential when you're doing this sort of thing, because you can never guarantee full wetting of your film. And so running it through a plasma treatment, running it through a corona, maybe dipping it in a solvent, that can change the surface energy substantially, and it can really improve. Then the ink side, then can you add a surfactant into it without damaging the efficiency or the performance? That might change the ink's surface energy. So you really, when you're running your contact angle, you really want to see that flatten out nicely, or in some cases not, if you really want to have a sharp edge. So it's really knowing what you want.
Yeah. Well, actually, just following up on that, I guess, and this also goes a little bit to, you know, some of the other kind of toxicity considerations that you discussed in terms of the ink formulation. But this, you know, questions around essentially the ink stability, right? You know, once you've actually formulated it, how long can you use it, and how much of that kind of shelf life kind of thing is something that you guys consider quite a bit, consider in your essentially your process design? Is another one of the questions.
Really, really great question, and really important. So my answer is, we think it's really important. We don't work on it. We hope that other people are doing it, but it is going to be incredibly important. if we really want to see, if we really want to see terawatt production, then we're going to be buying more than just vats of this stuff. And those vats we're not going to be able to be making fresh. So I think if somebody's work is on, showing that an ink is stable on day one and stable 6 months later, I'd want to read that. So I think it is valuable work.
So one of the other questions we had is kind of how bifacial is the carbon electrode device, and I guess this also goes to, you know, there's a lot of emphasis from various places on going to tandems, but I think, you know, you provided kind of a really lovely vision for how the world is more than just that. But yeah, just a little bit on kind of to what extent, you know, that carbon electrode really sets kind of the directionality of your device and how much flexibility you feel like you have there.
Yeah, so I mean, from a perspective of its, well, simply its transparency, of course, it's zero. So from bifacial mechanisms, then that doesn't apply. So they're not bifacial, unfortunately. They're always coming in through the TCO side. That's not to say that alternative carbon materials can't be bifacial, and we're starting to see graphene materials and layered graphene oxides starting to come in and you know, and silver nanowires, you know, as transparent electrodes. So this particular carbon is just thick.
Yeah. So I mean, but I guess from a conceptual perspective, right? I mean, there's also the opportunity in principle to use some of the same kind of architectural elements, but maybe with materials who have a different kind of absorption profile, but can still kind of provide that scaffolding. Is that something you guys are actively looking
absolutely.
at?
So one of the projects we have is also working with the steel industry to look at whether there's a viable product to be able to go from coated steel right into perovskite deposition in one production process. Now, last time I checked, steel itself isn't transparent. At least I haven't cracked that one yet. So you're always going to have, unless you laminate an upside down PET system. If you want to do direct deposition onto steel as part of the final step of painted steel at the production plant, which is again, the UK produces 200 million square meters of coated painted steel every year, then you're going to have a really robust transparent electrode. And so we do have work in that area to try and understand that. And that's where I think, and I work on solution processing, but I'm not anti-vacuum, I'm not anti-vapor deposition at all. That might be where we end up hybridizing our process as well. Yeah.
Well, you're probably old enough to remember the Star Trek movie where Scotty came up with transparent aluminum. That's clearly what we need.
Yes.
You know, but
all right. So I was wrong. Sorry. Yes, we will do it in the future.
I don't know how, but all right. Let's actually I will also share one comment from one of the. It's more of a comment than a question, but was basically that, you know, this particular participant said they don't very often, you know, agree with people on these things, but basically agreed with everything that you had to say and really kind of, you know, appreciated the context and this the focus on some of these aspects of roll to roll and the advantages that are presented there. I guess one of the other questions that I'd have, given your experience, is, I mean, you've shown how adaptable the perovskites really are to the process. I guess I was curious about, you know, where that line is, where, you know, having some purpose-built tools also becomes an important kind of aspect of basically pushing the boundaries on that. Yeah. And indeed, you know, a little bit on, in the context of your experience on, you know, where you try to find that line of when it is time to basically start evolving the tool that you're actually using.
Great question again. And, you know, there's always a danger in startup companies, for example, about freezing the system and freezing the architecture. You can't not ever freeze it. Sometimes you just have to say, right, this is what we're building towards. But in the universities, we have the luxury of never having to do that. And I think that's where we can play a real role, is that whilst some incredible work is being done in some startup companies and beyond to really push that TRL 5, 6, 7 area, we should be following behind to update on those equipment, to update on those material sets, and informing that industry in partnership to try and develop those things. And a good example of that, I think, is that, you know, we know that we can heat perovskite in a gas-fired oven or in an IR oven, but there's been some very nice work over the last few years, and we've contributed into that for photonic processing. You know, we can process perovskites in, you know, milliseconds if we wanted to. But that, I'm not necessarily convinced that would be the approach that a startup company would want to take from the first moment. So we do want to develop those things. And I think that's the role for universities that don't have the pressure of delivering a prototype with a certain value, for example, is to develop those tools for it. You know, and not just tools for manufacturing, but, you know, I regularly use the perovskite database that's been set up, you know, just to understand the trends. And unfortunately, because it finished in sort of 2020, I think, was when it was most updated. This one that came out of a European effort, but it involved worldwide. It's still really great for me to be able to use that as a tool. So not just physical tools, but online tools as well.
Yeah. This is the HZB database.
Yes, that's right.
Yeah. Yao, do you have any questions? Or like I said, I'm happy to continue.
There was a question earlier that Kelly asked in the Q&A that I think is very interesting about how the most efficient and stable cells often have spin-coated passivation, interlayers, and selective contacts. You know, now these SAM layers, the phosphonate layers, and those sort of things. And do you have any insight or idea how to make those viable for scaled-up solutions?
Yeah, again, brilliant question, because this is the exact conversations that I'm having with my team. We sit down, we go, right, okay, so somebody's telling me that SAMs are the next big thing, that 2-packs is the next big thing. How do we slot die coat that? And so we send off our team to have some trials. They may or may not be the right thing. And it turns out that they are very difficult to do. They're some single layer. You know, other things like 2D, 3D, 2D composite type structures. How do we do that? It's not even trivial to put to slot die coat PEA to PEAI down onto an existing perovskite. So these are our current, as in Thursday, challenges to try and boost the efficiency of perovskite by understanding, are all of these wonderful extra bits and pieces processable? I don't have the answer. I do know that we haven't. It's whenever we go into the lab and do the whole let's just try it and see, it very rarely works.
Mm-hmm.
So there's something that needs to be done. It might be, for example, dipping it instead of, but then you've got to have to
the bath that it goes through. Yeah,
but then you'd have to remove all of the other monolayers on top. So whether you'd have a bath followed by a blow or something like that, you know, these are the conversations we're having.
Very cool.
Yeah. Well, we are right on time. So Tristan, just thanks again for a really inspirational talk. I will for sure be needing to, you know, up my acronym and game in the context of coming up with really both, like I said, clever and inspirational kind of names for stuff. But with that, we'll let you go. But thank you again for that really excellent presentation.
Thanks so much for the invite, and good luck to you all.